video, we consider yet another type of test that is based on the chi-square distribution, namely test of independence in a two-way table. An overarching term that is used is contingency analysis. And what does it involve? Basically, we have two categorical variables, and our interest is to test for the dependence or absence thereof of the relationship between two categorical variables. In other words, we're saying if we have one categorical variable, caffeinated coffee consumption at different levels, and clinical depression, does it exist? Yes or no? Our interest is to look at if there is a relationship between different levels of caffeinated coffee consumption and what the different classes of clinical depression. So, what is the context behind this data set? And why would we want to use contingency analysis? As I stated earlier, we're trying to look at the relationship, if there exists one, between two categorical variables. The context here is specified in this example. Let's read through that. Researchers conducted a study investigating the relationship between caffeinated coffee consumption and the risk of depression in women. So we're looking at the relationship between two categorical variables, as the table illustrates, and they collected data on 50,739 women free of depression symptoms at the start of the study in the year 1996, and these women were followed through 2006. The researchers used questionnaires to collect data on caffeinated coffee consumption, asked each individual about physician diagnosed depression, and also asked about the use of antidepressants. The table below shows the distribution of incidences of depression by amount of caffeinated coffee consumption. So, for caffeinated coffee consumption, it's a categorical variable for those who drank one or lesser cup of caffeinated coffee per week, those who drank between 2 to 6, those who drank 1 cup per day, 2 to 3 cups per day, and greater than or equal to 4 cups per day. Well, this table, as you might recall, is called a contingency table or a joint frequency distribution table. We learned that earlier in the semester. And that leads us to a contingency analysis, which is a test of dependence between the two categorical variables whose data points are summarized in the contingency table. So, question A, what type of test will be appropriate for evaluating if there's an association between coffee intake and what depression? That will be the chi-squared test of independence, not the goodness of feet this time, but the test of independence. Uh, this test is also called a test of association between two categorical variables. And the next step will be to write out the hypothesis for the test. The null hypothesis will be the case of independence, that is, caffeinated coffee consumption and depression in women are not connected or associated or are independent, versus the alternative that caffeinated coffee consumption and depression in women are associated or dependent. This would be the null hypothesis and the alternative. Part C. We would like to calculate the overall proportion of women who do not suffer from depression and those who do suffer from depression. So let's start with those who do suffer from depression from the table. So going to the table, we look at the yes category. Those who do suffer out of the entire population. So that will be 2607 out of 50,738. That will give us about 0.0514, representing about 5.14% of the women who do suffer from depression. And the proportion who do not would be the 48,132 out of that number. That is the same as simply saying 1 minus 0.514, and you get 0.9486. Then we would like to look next at the analysis here. We'd like to look at testing the null hypothesis versus the alternative. That requires some form of mechanics or computation. Now, to get us started, to use our chi-square test statistic here, the chi-square test statistic remains that we're looking at the observed values minus the expected values squared all over the expected value for each observation. Well, that means that each of the observations here, which I'm highlighting in yellow and also in red, I want to distinguish that from the totals because the totals are derived from the observed values. Okay, and in order to compute the chi-square test statistic, the OIs are each of these values. These are the observed values. We will need to compute the corresponding expected counts for each of them. When we're conducting a chi-square test of independence, the correct way to compute the expected count is to use the formula row total multiplied by column total divided by a grand total. Let's take an example. So in question D, we're to identify the expected count for the highlighted cell. Let me erase this a little bit. The highlighted cell is 373 as an example. So the observed value OI, our OI here is 373. I'm going to write it here. So I have 373. Excuse me. Let's take that back again. My bad. I was already going on into the expected value and the expected counts. We want to look at your 373 and we want to look at the row total. That is 2607. So that is 2607 multiplied by the column total. For that cell, the column total was 6617 all over the grand total, which is 50739. So that will give us approximately about 339.9854. So this will go to approximately 340-ish. Well, that was the expected count for 373. We will need to do the same for each of the highlighted observed values. We need to do that in order to get the total expected, the individual expected count, and later to look at the entire chi-squared statistic. What this means is, after getting the expected count for one, I can also get the contribution of this particular cell to the test statistic using the chi-squared test statistic formula. In other words, I would say what was observed was 373 minus what was expected was 340 all squared divided by 340, and this will give about 3.20. Now this will be the contribution of this particular cell to the overall chi-square test statistic. But we'll need to do this for every observed value. So how do we do that? Well, that takes us to question E, where we'd like to find the value of the test statistic. I have taken the data set here, and I have it in StatCrunch right here. So let's zoom in here a little bit. So I have 670, 373, all of the values in this row. Here they are, and they all have the corresponding row total 2607, and the individual column totals for each of these values are 12215, 6617, 17234. All of them are here. And I have a repetition of all of the grand total, which is 50,739. So I would like to enlist the support or the use of StatCrunch in order to compute the expected count for each of these observed values. To do that, I'll go to Data, and I'll go to Compute, and I'll go to Expression. So click on Expression, and in this case, click on Build. We want to build an expression here. I would like row total times column total. I'd like that to be in parentheses, just working with my PEMDAS. So I'm going to activate parentheses. Then I'll go back in here, and I want to key in here. What do I want? I want the row total. So row total first. I'm going to double click on that. All right, that didn't work out well there. So let's do row total and times what? Column total. So times the column total. Double click on that. And I like to close that parenthesis and say the result divided by the grand total. So divided by the grand total. And I would like to OK that and build it. Let's see that again. Why do we have that? Yes. Column label, I can call it expected column, and let's compute. Good. And that's it. You will notice that for 373, the one we highlighted earlier, which we computed by hand, we got 339.9854. That value is right here. The beauty of StatCrunch is that it has computed for every cell in one go. All right. Now, with that said, now we have the observed, which is our O, the expected, which is our E, I's, and to get the value of the test statistic, we will need first the degree of freedom. So what is the degree of freedom on the test of independence? It will be number of rows, which are denoted by R. That will be 1, 2. So that will be 2 minus 1 multiplied by number of columns. 1, 2, 3, 4, 5. So that will be 5 minus 1. So this is 1 multiplied by 4. That is equal to 4. So I'm working with 4 degrees of freedom. And my value of the test statistic can be obtained from StatCrunch. All I need to do is go back to my chi-squared. So go to statistics, back to goodness of fit, go to chi-squared test, and indicate that the observed value, the observed column, is all values under the observed column. And my expected, select the column expected. And in this case, I'd like to compute. The only thing I need here, please be wary, is this value. This is my chi-squared test statistic, 20.965688. Take note that my p-value in this case is not equal to this value, because if you look at the degree of freedom, it does not match the degree of freedom we have here. This was assuming that we're conducting a goodness of fit test. That is not what we're doing. We have only used StatCrunch to compute or to utilize this formula to get us to this value. Okay, so the real only valid value on the test of independence is this chi-square value. Now we're going to take this chi-square value. I'm going to cut this into memory. I'm going to copy, and I'm going to close out of this. Go to statistics, go to calculators, and I'll go to my chi-square calculator. It will require the degree of freedom, which is 4. So I'm going to write 4 here. Make sure that this is an upper tail test, and I am going to paste the what? The test statistic value right here. Okay, and I will compute. So I can see this is a very small probability, which is 0. So this is equal to 0.00032167. Okay, and with that said, with that p-value, I'll take it into the decision making what platform, and I compare the p-value as usual, 0.00032167, which is definitely lesser than alpha, the level of significance, if it is set at 0.05. And when the p-value is lesser than alpha, of course, we reject the null hypothesis in favor of the alternative. Let's go back to the alternative hypothesis. So we are favoring the alternative. So what's our conclusion then? Along the lines of caffeinated coffee consumption and depression in women are associated. So in other words, we conclude that the data provides convincing evidence to suggest that caffeinated coffee consumption and depression in women are associated. Then there's question G. One of the authors of this study was quoted on the New York Times as saying it was too early to recommend that women load up on extra based on just the study. Do you agree with this statement? Explain your reasoning. The answer should be yes. It is too early. And why is that the case? That is because this is an observational study. Remember, in an observational study, we cannot draw cause and effect what conclusions. This means that based on the study, we cannot deduce that drinking more coffee just leads to less depression. And that is because in the case of an observational study, we have not controlled for other possible extraneous factors, otherwise called locking factors, that can cause what? Decreased depression in women that drink what? Coffee. So one has to be wary. We can only talk about them being associated, not one leading to another. That brings us to the end of that question.